Testing. Mic check. 1, 2, 1, 2. Books. Let's go. Go. Let's go like this. Oh no. Let's do. Okay, so we'll get started in just about a minute. Ooh. Ooh. All right, gentlemen. All right, so welcome. How did homecoming go? I didn't participate in anything. Did we win? Who did we play? Did y'all see any celebrities? Anybody got any interesting stories that they're willing to share? But if not, it's okay. I just kind of, I don't know, I always be enjoying my time. Either I'm gaming or like running around town or hanging out with people. That's usually what I'm doing. Let me see. So yeah, we're continuing forward with our usual, every day. So last week we did section 2.1, right? I think it was combining functions and composite functions. So today we're gonna do more exploration of functions with polynomial functions, right? Yeah. So section 2.2, polynomial functions. A few objectives here. 1, learn properties of the graphs of polynomial functions. 2, determine the end behavior of polynomial functions. 3, find the zeros of a polynomial function by factoring. 4, identify the relationships between degrees, real zeros, and turning points. And 5, graph polynomial functions. Okay. Oh, yeah. There we go. Okay. So a polynomial function of degree n is a function of this form where n is a non-negative integer and the coefficients an minus 1, all the way to a naught or a 0 are real numbers where an is not equal to 0. All right. Another way you can kind of articulate a polynomial function. Polynomial functions are a finite sum of monomials. And what's a monomial? A monomial is a one-term. Let me see. A monomial is like a power function where we have some real coefficient times a variable x raised to a non-negative integer power. So examples of monomials would be things like we got the number 2, 7, 3x squared, 5x, 10x to the power of 15, stuff like that. Give me just a moment. Okay. All right. So a monomial, one term, it's a polynomial with one term, but again, it's a one-term polynomial or expression or equation that takes on the form we have some real coefficient times a variable x raised to a non-negative integer power. All right, so then a polynomial is a finite sum of monomials, right? Okay. So the term a n x to the n is called the leading term. The number an is called the leading coefficient, and a naught is called the constant term. A constant function where we have f of x equals a, where a is not equal to 0, may be written as f of x equals a times x to the power of 0. This is a polynomial of degree 0. But the 0 function, f of x equal to 0, has no degree assigned to it. This is because, the f of x equal to 0 can be written multiple ways, right? You can write it as like 0, but that's the same as 0x squared, but that's the same as 0x to the power of 0. Because the degree is not constant, then that's why we say that this doesn't have a degree. So when you have f of x equals 0, again, there's no degree assigned to this. But f of x equal to some number other than 0, those can all be written as a times x to the power of 0, right? Okay, so don't read too much into that. It doesn't really pop up that often. Polynomials of degree 3, 4, and 5 are called cubic, quartic, and quintic polynomials. Why'd you stop? So let me see. This expression, this finite sum of monomials, is a polynomial. The function f of x defined by f of x equal to that polynomial is called a polynomial function. And then the equation where we have a polynomial equal to 0 is called a polynomial equation. So, we're just identifying a polynomial and then a polynomial function and a polynomial equation. So common properties of polynomial functions. The domain of a polynomial function is a set of all real numbers. So in general, once we identify a function as being polynomial, then in general, the domain is all reals. The graph of a polynomial function is a continuous curve, right? So if we're viewing the image on the left, there are no breaks or holes or gaps. So that's indicative that we're working with a polynomial function. So that's an example of a continuous curve versus the image on the right, we have that hole or gap, right? So if we have a hole or a gap or anything like that, then it's not going to be the graph of a polynomial function. So that's an example of a discontinuous curve. This cannot be the graph of a polynomial function. Okay. So again, as we make our way through these, if anything isn't clear, feel free to get my attention and we can talk about it or type in the chat. I am monitoring the chat. Let me see. Yeah. Okay, let's keep going. So another property of the graphs of polynomials is that they are a smooth curve, right? So the image on the left, all the curves are smooth. It's a continuous unbroken line. So another way to kind of conceptualize continuous, you can put your pencil at any point on the graph and you can get to any other point on the graph by tracing the graph without having to pick up your pencil. In this example here on the right, if we put our pencil on the left and we try to get to the far right, we'd have to pick our pencil up to jump over that gap, right? So then that means that it's not continuous, so it can't be the graph of a polynomial. And so in this example, again, the curves are smooth. The image on the right has sharp corners or edges. So if the graph has a sharp corner or an edge, then it can't be the graph of a polynomial. So the takeaway from these last two examples, that's what, is that the graph of a polynomial is going to be a smooth continuous curve with a smooth curve, a continuous graph with smooth curves, right? So no breaks or holes or gaps, no sharp corners or edges. This image on the right, we identified several sharp corners or edges or sharp turns, so it can't be the graph of a polynomial. Okay. So state which functions are polynomial functions. For each polynomial function, find the degree, the leading term, and the leading coefficient. Okay. So in part A, that's a degree 4 polynomial, right? It's a finite sum of monomials. So 5x to the 4 is a monomial. Negative 2x is a monomial, and 7 is a monomial. So then we have a finite sum. Finite meaning the opposite of infinite. Infinite goes on forever. Finite, it stops at some point, right? In part B, without that restriction on the domain, it would be a polynomial. But because of that, remember, one of the properties of polynomials is that the domain is all reals. So because we have a restriction on the domain, then it's no longer a polynomial. It's not the graph of a polynomial. Or it's no longer a polynomial function because of that restriction on the domain. So A is a polynomial function. Oh, okay. So then because it is, for part A, because it is a polynomial, it asks us to find the degree, the leading term, and the leading coefficient. The degree of a polynomial is going to be the exponent, the highest power on any variable, right? So if we're looking at A, the degree in that instance is going to be 4, because the highest power on any variable is going to be 4. The leading term is the term with the highest power. So that's going to be the leading term is going to be the 5x to the power of 4. That's our leading term. And the leading coefficient is the coefficient of the leading term. So the leading coefficient is going to be 5, positive 5. Okay. So that actually gives us a lot of information about the shape of the polynomial. All right, I think we're gonna get into that a little bit later. Okay. So again, the degree is 4, the leading term is 5x to the 4, and the leading coefficient is 5. And then g of x is not a polynomial function because its domain is not all reals. Okay. So a function of this form, we kind of mentioned this earlier, this is called a power function. So we have f of x equals a times x to the power of n. This is called a power function of degree n, where a is a non-zero real number and n is a positive integer. Okay, so power function. So power functions of even degree. So given a power function, if n is even, then let me see, this is a test like symmetry or even or odd. Did we talk about that? The definition of an even function, right? So remember the definition of an even function. Let me see, f of negative x. When we evaluate f of negative x, it returns us back to the original. So here they replaced x with negative x, and then because n is even, right? If we evaluate f of negative x, then that's going to be equal to, let me see, a times negative x to the n. But because n is even, that becomes positive, which takes us back to the original, right? So that's the definition right here. We started with f of negative x. Again, because n is even, we're able to do this, and we get back to the original. Then that's the definition of a function being even. So the graph is going to be symmetric with respect to the y-axis. The graph of y equals x to the n, where n is even, is similar to the graph of y equals x squared, right? So we're working with an even power function, you know, is even, so it's going to have y-axis symmetry, things of that nature, okay? So then if we consider a power function of odd degree, right? So now we want to show that when n is odd, when we evaluate negative x to the power of n, we finish with negative x to the n, right? So if we evaluate f of negative x in this sense, then that means we're going to have this, a times negative x to the n. Because n is even, we can rewrite this guy as this guy, which is the same as negative times the original. And so this, in conjunction with this, is the definition of a function being odd. So that means the graph is going to be symmetric with respect to the origin, right? So it's going to kind of take on like an S shape. Whenever we have x comma y, we're also going to have negative x comma negative y. The graph of y equals x to the n, where n is odd, is similar to the graph of y equals x cubed. All right. So we can use, so now what we're doing, we want to explore the general shape of these power functions, right? We've explored two different cases where we have an even power function or an odd power function, or a power function to an even degree versus a power function to an odd degree. So we're going to have a total of 4 cases. The first case, let me see. Looks like we're missing something. So this should say, this is when n is even. Like this. So we have a positive a, and n is even. So then when we have a positive leading coefficient and an even power function, so if you think of like the graph of x squared, it kind of makes this shape, like a U. With a positive leading coefficient, what that tells us is that our graph goes up to the right. Because it's even, the other side does the exact same, right? So if you think even power function, just think of like the parabola. A positive leading coefficient, we know the parabola opens up, but to be a little bit more specific or a little bit more precise, when the leading coefficient is positive, that tells us the right-hand side goes up. Because it's an even power function, the other side does the exact same thing. So up to the right, up to the left. Okay. And then this is still n is even. Okay. But now we have a negative leading coefficient. So a negative leading coefficient tells us we go down to the right because the power function is of even degree. The other side does the exact same. So it's going to go down to the left. Okay. So then now we probably want to consider when n is odd. We're going to go back to a positive leading coefficient. But we want to consider when n is odd. That's not what I'm going for. Okay. So again, positive leading coefficient, it still holds. That means we go up to the right. But because the degree of the power function is odd, the other side does the opposite, right? So if we go up to the right, that means we're going to go down to the left. I just realized, hopefully that doesn't make too much background noise. But yeah, so a positive leading coefficient. So the leading coefficient tells us about the right-hand side of the graph. The degree of the power function tells us about the left. If the leading coefficient is positive, we're going to go up to the right. If the leading coefficient is negative, we're going to go down to the right. If the degree of our power function is even, the other side does the exact same. So even I equate with exact same. If the degree of our power function is odd, the other side does the opposite. All right, so we got one more case, and let me duplicate or copy and paste. Okay. All right, so now we have a negative leading coefficient, and the degree of our polynomial is odd. Negative leading coefficient means we go down to the right because the degree of the polynomial or the power function is odd. The other side does the opposite, so it's going to go up to the left. Okay, so this is the kind of information that we're getting from the power function. Okay, so we have some real coefficient times a variable x raised to a positive integer. Right? And we had those four cases. So now we want to consider this polynomial function of degree 3. We want to show that this polynomial is approximately the same as the power function 2 to the x cubed when the absolute value of x is very large. Okay. So let's start with our polynomial, which is this 2x to the third plus 5x squared minus 7x plus 11. And what we'd like to do here, let's factor out x cubed from all terms. So if we factor out x cubed, we're going to be left with 2 plus 5 over x minus 7 over x squared plus 11 over x cubed. Okay. So all we did was factor out x cubed from each term. So now we want to consider as the absolute value of x gets really large, right? So we'll say something like, let the absolute value of x tend to infinity or get really large. So as the absolute value of x gets really large, what happens, right? As the absolute value of x gets really large, if we have 5, like, just kind of think about this real quick. Like let's consider this term here, this second term, this 5 divided by x, right? We want to see what happens to that guy as the denominator gets bigger and bigger and bigger. if we have 5 divided by 1, think about what the result is. 5 divided by 1, right? Now think about 5 divided by 2 and what the answer is. Think about 5 divided by 5. Think about that answer. Think about 5 divided by 10. All right, you should get it. It should be simple. Think about 5 divided by 20. 5 divided by 100. Right? 5 divided by 1,000, right? So what do you notice about those results? As that denominator is getting bigger and bigger and bigger, what's happening to those outcomes? They're getting, hopefully you're thinking smaller and smaller and smaller, right? So with a fixed numerator and those denominators tending to infinity, the behavior is going to be the same in all three of those cases. So as the absolute value of x gets closer and closer to infinity, this guy gets closer and closer to 0. Same argument for this guy, and same argument for this guy. So as the absolute value of x gets closer and closer and closer to infinity, or gets bigger and bigger and bigger, those terms get smaller and smaller and smaller. In other words, they tend to 0. So then after that, then ultimately we're going to have that this polynomial is going to be approximately equal to 2x cubed, right? So then what we're saying is that as we go off to the far right, as we go off to positive infinity, the original polynomial essentially behaves similar to the power function 2x cubed. Now we just saw in the previous 4 cases, right? We know how the power function behaves. Notice it has a positive leading coefficient. So that means we should go up to the right. The degree of the power function is odd, so that means the other side does the opposite. So that means that in the long-term behavior, we're going to go up to the right and down to the left. And a similar argument can be made for negative infinity. We kind of showed it as we go up to the far right. We can do something similar for going off to the far left, right? So what this example gives us is that it actually leads us into this concept called the leading term test for polynomials, right? So given a polynomial function, the long-term behavior of the polynomial is going to be determined by that leading term. It's going to behave similar to the power function defined by that leading term, if that makes sense, right? Because of this argument here. Okay, so this was us just kind of, doing it ourselves, and then here's a type version of what we just experienced. So if we start with the polynomial, when the absolute value of x is very large, those terms tend to 0, or they get really close to 0. So then our polynomial is approximately equal to 2x to the third, or the power function 2x to the third, right? And again, in the previous 4 cases, we saw how that power function is going to behave in the long term. And so our claim is that our polynomial is going to behave in a similar way in the long term. And again, that leads us into what's called the leading term test. I woke up this morning, my mouth was like extra dry. Like I brushed my teeth. I don't know. It's just weird. It's just weird. Like every day, it's like I wake up, okay, what's today gonna be? It's like, is that all you got? Come on with it, Anywho, and it's like anything I think to try to like wet my palate just seems like it dries it out. It doesn't sound appetizing. Anywho, and I'm not hungry or anything. I've been drinking water. Okay, this is a little tangent. So one of the content creators I follow on YouTube he goes by Real Nagas. He basically like every Saturday he kind of does like he just reviews current events. He's just in front of his camera just talking about it, reviewing current events and just different topics or whatever. And so in one of his recent posts in the past few weeks, he mentioned something about alkaline water. He was like, be careful about doing too much alkalinity in your water because it can cause like indigestion and stomach issues. I was like, God damn it. I think that might be the source of my indigestion. So like for decades, I've been going to the same water spot, not thinking anything of it, just maximizing the pH, and I'll mix it and kind of go about my way. But I was like, man, I'm not eating anything. Why am I having such digestive issues? I never thought that like, the source of it might be I'm making my water too alkaline. And when he said it, I was like, dang. So I'm actually about to go get some water in the next week or so. But this will be the first time in like decades that I was like, okay, I'm not gonna do any pH. I think he recommended like, I don't know if he said spring water But he was like, you kind of have to add electrolytes to your water. And again, I'm no nutritionist. You have to do your own research. I'm just kind of sharing what my experience has been. So, I don't know how. I haven't officially changed it, but that's coming. I'm about to. And it's kind of weird because I don't know if it's true or not, or I don't know if it's psychosomatic where because I know I'm going to make that change, I have noticed an adjustment just because I shifted my consciousness and a shift in like digestion or whatever. So anyway, I don't know which came first, the chicken or the egg. I don't know which came first, changing the pH or me believing in changing in the pH, right? That causes the healing. And there's a lot of evidence that shows that it's just changing your mind will heal. Like you don't even have to necessarily change the treatment, but if the person believes it's going to change, there's a lot of evidence that supports that it's all mental. So guard your mind. Okay, anyway, so that was enough of that random tangent. So the leading term test, right? So we saw the 4 cases for the power function. We can extend those 4 cases to polynomial functions based on that previous example that we had. So given a polynomial function where the leading coefficient is not 0, where the leading term is an x to the n, the behavior of the graph f as x tends to infinity or negative infinity is similar to one of the following 4 graphs and is described as shown in each case. The middle portion of each graph indicated by dashed lines is not determined by this test. So this test we're about to witness, it doesn't tell us anything about the middle of the graph, but it tells us like as we tend to positive infinity or as we tend to negative infinity, what's how our graph is going to behave, right? That's essentially what this is going to tell us. So, okay, guess we still need that thing. Let me see if I can, let's see what I'll do right here. Paste, nice. Undo, copy, delete. Okay, right? Let's paste. This is when n is even. So the first case, we have a positive leading coefficient and our n is even. Positive leading coefficient means the graph goes up to the right. So as we go off to positive infinity, the graph is going to go up to positive infinity. Because n is even, the left-hand side does the exact same thing, right? If you guys could see me, I probably have my back to you because I wanted to show going up to the right, or I might reverse my image. But, I got my hands up like I'm a football referee saying goal, right? Goal, right? Just for a visual image. But again, a positive leading coefficient, it goes up to the right. And because n is even, the other side does the exact same. So we're going to go up to the left. Okay, so that's the first case. Similar to the power function. In the middle, this doesn't tell us anything about the middle of the graph, but we have a sense of what happens as we go up to the right and as we go up to the left. Okay. Okay. Let's paste. Let's crop what we don't need. So now here n is even, and we have a negative leading coefficient. So negative leading coefficient means we go down to the right. When n is even, the other side does the exact same. So it's going to go down to the left, right? Again, this doesn't tell us anything about the middle, but we know as we go up to the far right, y tends to negative infinity. As we go up to the far left, y tends to negative infinity. Okay, so just like the power function. Okay, and then paste. So when n is odd, so positive leading coefficient and n is odd. Positive leading coefficient means our graph goes up to the right. N is odd means the other side does the opposite. Odd means opposite. So if we go up to the right and our n is odd, then we're going to go down to the left. Okay, that's case 3. And case 4 is the reverse. Let's paste. Delete. N is odd. The negative leading coefficient, it goes down to the right, up to the left. Odd means opposite. Okay. All right. Hopefully we're all aboard and we're not all bored. Let's keep going. So here we're actually using the leading term test to determine the end behavior of the graph, right? So we're given this polynomial function. First question is, Here, I'm gonna make a quick quiz because I would like some feedback. So for the quick quiz, let me see. I'm gonna write quick quiz. That's fine. I want A to be this guy, actually. Let's do like this. B, this guy. C, this guy. Okay. All right, so what I'm gonna do, let's see, no, I can't do it there. Gotta do it. Sure. Close. Let's see, polls and quizzes. Not the 25 question one. Oh, let me give an update about that real quick. So I know we were kind of testing out. Now, more than likely, that's how I'm going to run my Wednesdays. I think you all were my trial course with the multiple questions, and it is what it is. As long as because it was a trial, it was full of like hiccups, and as long as I had there were some signs of life. Like if you at least attempted questions, even if you didn't get them right last time, or if you were just in the Zoom call, then I gave you attendance credit. We're going to do something similar on Wednesday. So by my third class last Wednesday, I ended up making like a quiz. Like my second class, I made a quiz that had like 25 questions on it, right? And so you'll experience it on Wednesday. Um, but what happened was what had happened was the way this was set up. Um, we were going through some questions, and the students hit submit. I was like, damn. So they hit submit too early before we got to the end. So I had to like think on the spot. I kind of scrubbed that one and kind of gave them credit for, again, as long as they showed signs of life, gave them credit. Some people were MIA, so everybody didn't get credit. Some people, it just MIA. But by my third class, I did an iteration or a confirmation. It's like it seemed like it worked. I made it so that you'll experience it. I had something essentially working by the third class on Wednesday. So more than likely, we're going to do something similar on this upcoming Wednesday when we do our homework review. Okay. But we'll see that on Wednesday. The one we like to use right now is this one. Launch the poll. Okay. So now, use the leading term test. Okay, what is the leading term? Is it A, 3x squared? Is it B, negative 2x cubed? Is it C, 4, right? So just I'll give you a full 30 seconds. Just take 30 seconds to identify what is the official leading term. All right. Just take a moment. Pull this up. That's looking good. Ooh, muy interesante. You sure? Uh-oh. 20 seconds. Let me see. Slow on the draw. I should have had this already going. I'm gonna pull up something now though. Right here. No copyright background gaming music. I will do this for the slide. What I'll do is reduce the volume. Come on. All right, let's let it ride. Okay. Oh, I think I got some people. I got you. Okay, I'm gonna go ahead and close the poll. I got at least one person. So B is actually correct, right? The leading term, right? Because I started to put it in the order it was given. I was like, let me mix it up, right? And I did that on purpose because sometimes they do give you the terms in mixed up order. So if you ever get a polynomial where it's not in descending power order, go ahead and rearrange it and put it in descending power order. That'll make things easier. Because if you just take it as face value, you run a chance of missing it, right? So B is the correct answer, right? So you guys got it. I kind of tricked. I was throwing a little bait out there to see if somebody would take it. So B is the correct one. Let's do like no, whatever. Be nice if I had a quick way to fill that. I don't know of a quick way to fill it. How big is that? That is too big. That's what she said. All right. Where is it? I'm looking for. Come on. Let's put you like this. Now, what we could do I didn't think about that. Let me see if I can get that to work. Okay, I know what I can do. Like this, like that, like that, like that. Oh, let me try one more time. So it does have a polynomial feature. Oh, did it do it? It did it. Okay. So then what I'll do, I'm gonna, here we go. Let's go style. I want that to be like that. Make it thicker. But then the fill, I want it something like this. A bit lighter. We'll just go with that. That's fine. That'll work, right? It's weird, but whatever. All right, so B was the correct answer there. Or let's do that, I guess. I'm not feeling that either. It just feels weird. Okay, we'll go with this. Okay, so that was our quick little quiz, right? So the leading coefficient there was the negative 2x cubed, right? Okay. Let me see. Let me write down that question just so we have it for reference. Quick quiz. Let me rewrite this. Say quick quiz. What is the leading term? So we got so it's B. Okay. Okay, so the leading term is the negative 2x cubed, right? So now if we go to use the leading term test, what does that tell us about the graph? Any brave soul feel like they can describe what happens to the right and what happens to the left? Any brave soul? I'm just curious. Going once, going twice. Okay. So with the leading coefficient being negative, that tells us we go down to the right, right? So with a negative leading coefficient, we're anticipating it to fall to the right. With the degree of the degree of the polynomial is odd. Again, the degree is the highest power on any variable in the polynomial, which is a 3 in this case. So because the degree of the polynomial is odd, that means the other side does the opposite. So if we're going down to the right, then that means we're going to go up to the left. So this doesn't tell us anything about the middle. We just know as we go off to positive infinity, y tends to negative infinity. As x goes to negative infinity, y tends to positive infinity. All right, so this is all that this is telling us from the leading term. Okay, that's a type that they just didn't produce properly. Let me see. This should be, those are supposed to be like right arrows. So like that. Let's do something like that. That's what that's supposed to be. Same thing here. Matter of fact, let me do like this. Copy. Paste. Serious? Duplicate. I'm just going to get rid of these typos. Duplicate. Duplicate. And again, these are supposed to be like right arrows. Style. Make it down some too thin. All right, that's decent. Precision. Style. Okay. Duplicate. Delete. Undo. Yeah. Duplicate. So that's really what this is supposed to be. Okay, so use a leading term test to determine the end behavior, right? So here, the degree of our polynomial is 3, which is odd. The leading coefficient is negative, so we're working with case 4. So the graph of f rises to the left and falls to the right. A negative leading coefficient makes it fall to the right. Odd degree polynomial, the other side does the opposite, so it should rise to the left. So as we go out to the far left, wait a minute, yeah. Y tends to positive infinity as x goes to negative infinity. Y tends to negative infinity as x goes to positive infinity. Okay, we got about 5 minutes. Let's just kind of keep going and hang out for about 5 more minutes. All right, so we have real zeros. As a matter of fact, I'm going to scan just to get to the end. Whatever I skip, again, you can find these examples worked out in my on my YouTube channel. So if you go to like our playlists that you should have access to, you go down to section 2.2 and you'll see anything that we skip. It should be worked out there already. You can see each example worked out in detail. So real zero is a polynomial function. If f is a polynomial function and c is a real number, then the following statements are equivalent. So if you ever hear us say c is a zero of f, that's going to be the exact same as c is a solution or root of the equation f of x equals 0, but that's the exact same as c is an x-intercept of the graph of f. The point c, 0 is on the graph of f, right? So the x-intercept, a solution, a root, or a 0, these terms are we use them interchangeable. They're all equivalent. They all mean the same thing. We're just saying the same thing essentially 3 or 4 different ways. Okay. So find all zeros. So this is where factoring will come into play. I think in the interest of time, I'm going to have to leave this as an exercise for you. So I'm pretty sure I have this worked out on my YouTube. We also have a typed version there. So I'm going to have to leave that for you. The intermediate value theorem. Let a and b be 2 numbers such that a is less than b. If f is a polynomial function such that f of a and f of b have opposite signs, then there is at least one number c between a and b for which f of c equals 0, right? So remember we had those properties of polynomial functions that they're continuous graphs with smooth curves. So there are no holes or gaps, no sharp corners or edges or anything like that. So then if we consider 2 x values where the first x value is strictly less than the second, so there's some kind of gap between them. And then when we evaluate f of a versus f of b and they have opposite signs, that means it has to cross the x-axis at some point between those x values. There has to be some c between a and b such that our polynomial function is basically the x-intercept, right? But somewhere between. So that's the intermediate value there, but it's a play on the fact that polynomials are continuous functions with smooth curves, right? It's a play on that. Okay. So notice that a on the left, the corresponding y is positive, and then b, the corresponding y is negative. So then it has, if we're working with a polynomial, at some point it has to cross the x-axis. And then the image on the right is kind of the reverse, but it's essentially the same idea. And then as long as we have opposite signs, and we're working with a polynomial, then as long as we have opposite signs in our y value, and we're working with a polynomial, then we're guaranteed at least 1 0, but there might be more than 1 0 between. All right. Show that this function has a real 0 between 1 and 2. So with these 2 different x values, we would find the corresponding y. Show that they have opposite signs. So then by the intermediate volume theorem, again, I'm going to leave that for you to kind of discover. That's in my videos. It's also typed here, so you can use this as well. Real 0 is a polynomial function. A polynomial function of degree n with real coefficients has at most n real zeros. So once we identify the degree of the polynomial, we have at most n zeros. Like if we were working with a degree 4 polynomial, we have at most 4 zeros. We're not guaranteed all 4 or any at all, but we have at most 4. Right? We're not going to have 5 zeros in that case. I find the number of distinct real zeros of the following. So with these examples, we got lucky because they're already factored, so then that makes, we don't have to factor it ourselves. So then we can quickly identify the number of distinct real zeros. But again, I'm gonna have to refer to my recordings. And then multiplicity of a 0. So sometimes the zeros occur more than once. And whenever we have like whenever a multiplicity occurs an even number of times, like if we had x minus 2 quantity squared, that means that two of our zeros, when x is equal to 2, we count that as two zeros because it's squared, right? So that's multiplicity of a zero. Again, I have more details in my recording. But when we have an even multiplicity, that means our graph is going to bounce off the x-axis. When we have an odd multiplicity, then our graph is going to cross the x-axis. All right, okay? That's the main thing there. So when we have an odd multiplicity, it crosses. When we have an even multiplicity, it bounces. So for instance, here, in this example, we have like, it's already factored for us, but that first factor, x squared, the zero there is 0, but it's counted twice because it's squared. When x is -1, that has a multiplicity of 1 because of the power. And when x is 2, it has a multiplicity of 1, right? So again, those details are available. I'm going to have to scan because we got a little over a minute. Local max and local min. So these are like turning points. Let me see. So in a graphical sense, the local max is basically like the peak of the mountain. So where our curve goes from increasing to decreasing, it's like the top of a mountain. That's what it's a local maximum. Local min is going to be like the bottom of a valley. So these are turning points. So on the left, we have a local max. On the right, we have a local min. The number of turning points is going to, if it's a polynomial of degree n, we have at most n minus 1 turning points. Okay. I'm going to have to piggyback off of my recordings for these. All right, let me do a quick synopsis of sketching the graph of a polynomial. I think we kind of mentioned something along these lines when we did sketching a graph of a rational function. So it's similar with a few augmentations, right? So a great place to start when curve sketching is your intercepts, and I would recommend starting with the y-intercept first. Oftentimes it's easier to find a y-intercept than the x-intercept. So you have your two intercepts. We can do a test for symmetry. So see if it's even, odd, or neither. We can use the leading term test. I guess I should write this down. Just a brief, like, first you can look for intercepts, right? Second, you can do a test for symmetry. No, I'm missing some stuff in there. So essentially, is it even or odd? Okay. We can use the leading term test. I'm going to abbreviate it as leading term test. And then a few additional points. Between and beyond your x-intercepts. I think when we did rational functions, we said between and beyond the x-intercepts and the vertical asymptotes. Here, we're not going to have any vertical asymptotes, so you can, a few additional points between and beyond the x-intercepts. Just a few additional points. And then lastly, we put it all together in a graph. See the clock, I'm trying to get you all out of here. Okay, so that's just for things to, and again, these details I'll go through in my recording. So I'm going to leave that. You definitely want to check those out. I think I do this one as well. Okay, so that's the last one. That's fine. Okay, are there any burning questions before we go our separate ways? While you think about that, let me go ahead and make a copy of this available. Well, I guess I'll do it in just a moment. All right, so let me see. So on Wednesday, come ready to do the quiz. I would encourage it. So it's a good idea to just be present and be ready to be engaged. I'm going to be kind of keeping track of everything. If there aren't any other burning questions, we're going to go ahead and end the session here, and we'll meet back on Wednesday, same time, same place for the homework session. And with that, we'll end the session here. From one beautiful mind to another. Have a great day, gentlemen, and I'll see you on Wednesday, same time, same place. Take care. Peace. Let's see. I want to share. Second, my music while loading this. Oh, that's too low for me. Oh, man. Loading up the notes for today. Getting ready to go outside and play. Walk the dog, have a good time. Feeling real good, feeling real sublime. Eat a good smoothie and make it real good. Going down the street, staying out of the hood. Notes, I'm sorry, I get lost. That's like extra slow. All right, just loading a couple of notes. All right, gentlemen, take care. Let me check the chat.